Okay. Let's do some sound checking, as always. Okay. All right, let me check again the mic and the volumes here. Should be fine now. How about that? Okay, thank you. All right, well, I guess we can start. Let me double check this. Test, test. Okay, much better now, probably. Okay, so I guess we can start. Welcome everybody to this first Intrepid Robotics Meetup. This is happening live, hopefully no technical issues as they usually happen. I'm Francesco and I will be presenting Intrepid, the Intrepid platform today, which is a series of components I will try to explain. Plus, in the second part of the presentation, I'm going to go to the most terrifying part of every demo, which is hands-on and essentially showing you things happening in real. And since this will be live, it will be even more terrifying for me. So let's hope that everything goes well. So let me share my presentation here. I will dedicate just 10-15 minutes maximum to explaining what Intrepid platform is, what is the motivation behind it, and of course what we have been building so far. So Intrepid AI is an artificial intelligence powered platform for autonomous robots that allows you to prototype, simulate, and deploy robotic solutions and capabilities for aerial robotics, basically UAVs and UGVs, so ground vehicles and drones in all their subfamilies. But of course, you can also implement the logic of a typical ground station or even satellite applications, because these are essentially computers without wings. So the logic can be implemented as well in Intrepid and interacting with actual robots. Who we are, these two guys here. I'm Francesco on the left. I have also Alex somewhere in Europe and very likely online as I speak. We are two senior developers, very active in the open source community, so most of our work can be found online, GitHub mainly, but also at some of the links that I will give you at the end of this presentation. Of course, we also have a Discord channel, also in the link, in the list of links at the end of the speech. So feel free to reach out. We're always happy to discuss, and especially if you're a very technical person, we enjoy nerding around. So as I said, Intrepid allows you to combine the three essential tasks of the typical robotics developer, right? So building, simulating, and finally deploying on the actual vehicle, on the actual robot. The way we provide these tools is via visual programming. So we have so-called low-code dashboard. But since we are coders, we like to code, and we believe that when you know how to code, you have a lot of flexibility. We also give the users the possibility to bring their own code. So you can code in Intrepid, bringing your own libraries. As you will see later, you can bring your own Python, C, C++, Rust, JavaScript, ROS nodes, whatever technology you believe can work for your project. And the nice thing that we believe now is nice is that you can combine visual programming and coding in any possible combination. So you can go to the two extremes, totally 100% visual or 100% coding, or a mix of the two. Now, the motivation behind Intrepid is very simple. As you guys know, I expect there are roboticists here listening. Robotics has become a beast field in the sense that there is a lot of abstraction, complexity, there is a lot of integration issues that you can definitely read in the logos that you can see on this slide. I guess the state of the art for many is coming from ROS 1, ROS 2. I've seen also combining ROS with Docker containers. And as you can understand, this essentially adds sometimes useless complexity for the project that you are dealing with. It's kind of shooting a fly with a cannon in many, many projects out there. And also orchestrating all these diverse technologies can be complicated, as you definitely know. If you start combining things from DDS, from Xeno, or any other pub-sub technology, NATS, or many others out there, don't let me start on which language you want to bring to into the equation. Mainly C, C++, and Python. This is kind of the state of the art in a way, if I can call it like that. But Python, what does it mean? You bring PyTorch for computer vision, you can bring TensorFlow or simple OpenCV. So, the choice is incredible. And of course, this is a good thing because there are many tools at our disposal, but it's also a problem in the sense that it's very hard to understand what to use when. And so the idea of Intrepid is to not remove, but let's say mitigate this complexity and handle it at your place. Of course, maintaining performance and efficiency in mind. Other things that we have seen not being present in robotics are integration that we just covered. There is also versioning and reproducibility. When it comes to versioning, the only thing that we have seen happening is versioning code. So Git, amazing. Can we build a Git for robotics? Because if your project is not just code, but it's pipelines, right? It's for example, think it about as a graph. So it's a complex thing that publishes, subscribes, you have code, you have modules, you have libraries, you have black boxes that you don't even dare opening. So can you version all this stuff together? That's the problem. And the last problem is reproducibility. Reproducibility is, we have seen this quite mature in data science and machine learning. If you guys are familiar with Airflow, Kubeflow, these are basically tools that are now very mature after about 20 years that allow you to create data pipelines and then you can reproduce them. Think about machine learning models. You cannot reproduce them alone. You have to reproduce them together with the data you have been training these models on. And so you have to version and reproduce data plus models. So these tools do exist in data science and machine learning. We don't believe they do exist for robotics. So that was the motivation that from which Intrepid started. The last thing, performance versus accuracy. Those who are familiar with the state-of-the-art simulation in robotics, for example, they choose Gazebo most of the time. They have to deal or call it trade-off between this and this. And most of the time they have to stick with a very low number of entities because obviously the more complexity you add to your simulated world, the less performance you get. And some simulations are even prohibitive. Think about swarm robotics, where you can have an indefinite amount of entities and actors. Running these simulations in these particular scenarios can be tricky, regardless of Gazebo or any other. Like every simulator has to deal with that complexity. Will have a hard time. So what is our vision is, of course, to provide a set of tools that will help the less experienced robotics developer who maybe know how the use case work from a high-level perspective, but at the same time, we want to empower the expert roboticists, those who can write code, understand the hardware, and many other aspects of robotics. We want them to speed up the development process and the development cycle. The last thing that we want is quite ambitious, which is bridging the gap between research and commercial applications. We all know that robotics is a cutting edge. It's a combination, in fact, of research and productization. We have seen that many of the papers that have been published in academia usually die the day after the nice trip to present them. When it comes to commercial applications, projects survive and live as long as the market decides. And if you're not fast there to translate the research into the productized application, very likely that project will die. Can we speed up that? Probably yes. Hopefully yes. So in a nutshell, and I really conclude this relatively boring part before the demo, of course. Can we provide? Can we simplify all this? First of all, the answer is yes. How? We provide with Intrepid an orchestration engine that allows you to combine and manage very diverse technologies. Think about having ROS1, ROS2. We have seen projects in robotics with ROS1 and ROS2 because they didn't have the capacity to or the bandwidth to migrate from one to the other. Standalone libraries, Python packages, computer vision stacks, networking, etc. Can we combine all these things into one model, which is the behavior, we can call it like that, or the capability? Who's going to orchestrate that? Okay. Last but not least, the ability to run on pretty much any architecture and any operating system. Those who come from ROS know very well what is the problem here. Marry an operating system because of dependencies can be a problem. Okay, and that's in fact an integration issue. So we want to solve that by running seamlessly on pretty much any operating system. And indeed, we already natively support Windows, Mac OS, so Darwin kernel, of course, Linux, and any architecture that you can purchase at the shop, from Apple M, ARM, x86, RISC-V, why not? There is a free download for you. This is the Intrepid orchestration. You can download from intrepid.ai/notes. It's a PDF in which we explain a bit what we mean by robotics orchestration. So how does Intrepid work? Before deep diving into the demo, let me explain a bit what's Intrepid and how Intrepid solves things. In Intrepid, everything is a graph, all right, which is at the center of everything. So what is a graph is an execution model. Let's start from there, and then we'll explain better. Around that graph, there is, as I mentioned, the low-code dashboard that I will show you in a minute. There is the efficient runtime that is basically the component that you run on the vehicle, on the robot, on the ground station, wherever you're in the field, let's say. And that is the runtime that will execute the Intrepid graph. Okay. Then, of course, we built a ROS2 integration, which I will show in the demo. It's called Intrepid ROS Bridge, that allows you to bring an entire ROS ecosystem into Intrepid and the other way around. And finally, the simulation engine, also part of the demo, that will be essentially the simulator that you can use with or without Intrepid. So as I will show you later, these are all components that you can choose to use or not use. So you're not, you don't have to marry the entire platform. You can date each component separately. The only case in which this is ethically acceptable. Okay, so what is the Intrepid graph? The Intrepid graph is what we call the Intrepid graph is in fact a hybrid computation model that performs the logic of other computation models, in particular behavior trees, for those who are familiar with non-playing character video game development. Finite state machines, these are the more reactive things. Roboticists know this very well. And generic execution graphs, think about graphs that compute numbers, okay? Number crunching. So think about lazy computation with PyTorch, TensorFlow. These are all lazy graphs that get optimized and then executed. In Intrepid, you can combine these three very different logics into one graph, okay? And that's the power, in our opinion, the power of the Intrepid graph. Once you have the graph, you can version, you can reproduce it, you can share, you can collaborate with other team members or other folks. You can do all the things that you can do with code, right? And yeah, this is the summary. We are coming after, so we provide, as I said, a very efficient runtime, deployable in any operating system. A microcontroller will come next, so you can run this. You will have the capability to run the Intrepid engine on the Intrepid agent on a microcontroller. And as I said, available for pretty much any architecture, hardware architecture. Okay, so enough talking. Let's get started with some visuals. So we go to the Intrepid platform. When you sign up and log in, for the record, you can sign up from here and download basically the two things that you need, in particular the Intrepid agent or the simulator. Once you are logged in, this is how the dashboard looks like, right? An empty workspace in which you have on the sidebar a library of nodes that are ready to be used, and of course the workspace right here that allows you to build your own graphs, nodes, and all the other components that your robot will execute. So, for example, I will show how in Intrepid you could, for example, here, well, you have mathematical operations, of course, if you want to do mathematics operations. So, for example, let's have an addition, another addition, or I don't know, a subtraction. These are the, baby steps. And the idea here is to, connect things, right? Now, of course, if you go to the nodes that we like the most, the robotics nodes, you find more complicated things. You can find an entire Mavlink library that allows you to use the Mavlink capabilities and the functions visually. You can find network nodes to send, receive via network protocols without implementing any. Of course, ROS, publishers, subscribers. We are adding actions and services as well. I will show you that later. Controllers, why not? Let's put a velocity controller. So let me see if I can show you something like super simple. And imagine you have a computation somewhere here that returns, let's say, altitude, yaw rate, Vx, and Vy, so a velocity vector. You give that velocity vector to the velocity controller. This is an abstraction of a real controller that we have implemented for the vehicles that I'm going to show in the demo of the simulator. But of course, once we are partnering with the robotics manufacturer, they can have their own controller, or they can have the usual PX4 controller widely used. This node will look like this, more or less, but it will be just an interface to the actual, the actual controller that you have. So let's say we have a timer. So usually you send stuff to a controller at 100 Hertz or with something like that. So what I'm doing here essentially is controlling a vehicle via velocity controller. Okay. Now, if you want logic like this, so this is like the low-level capability, of the robot. But you can also implement something like more high level. For example, think about the usual sequence in terms of behavior tree. So you can say something like on start, you start this, and then you can say, okay, I want to perform a sequence which is connect this task. The first you have to take off, so you connect to a takeoff behavior. This is a graph in my library in this case. So it's in the graph library. So you can attach to this task a takeoff behavior. And then you can say, okay, now I want another task, which is this. And of course, you can add as many tasks as you want. And this, I don't know, we have been at Tyros, so I guess we have an Iros challenge. There you go. That's it. So what I'm doing here, I'm implementing in the same graph a velocity controller and a behavior, a high-level behavior, in the same Intrepid graph, right? So this means that what you have in front of you is a multi-threaded application with real-time constraints or near real-time constraints, etc., etc. There is a lot of complexity behind this graph, right? Because there is a high-level logic, there is a low-level logic. They travel at different pace. If you have to write this with code, I strongly believe that it's you have to know what you're doing. That's what I'm saying. Okay. All right, cool. So let's go to another example that I prepared for this speech, which is this, which is, it looks simple as well, but it's tiny different because, so we have the usual velocity controller here, but in this case, we have this nav0 node, okay? And this nav0 node, as you can see here, you can read, it's written SDK. So this means that this node is not a normal node, like this one, for example. So it's not, we don't call it a native node, we call it it's an SDK node, which means that the logic of this node has been implemented in Python in this case, but it can be implemented in other languages. And the only thing that you see on the dashboard is the so-called signature of the node, which is the list of inputs and outputs. And then the logic is invisible. I consume this node as a black box because someone implemented this in Python. And if we look at what this node does, let me try to explain very briefly. This node takes an agent ID, a drone position from a GPS. So this is the abstract version of a GPS sensor. Drone velocity, GPS speed. We take angular velocity from an IMU. We take the goal position. This is more of a special node. It's like a map node. We can, so basically it takes a position on GPS where the goal is, and then it connects to an abstract node. This is the proximity node that detects obstacles, ground, vehicle, depending on what you want, and returns, first of all, what it is, and then the position where that obstacle is. So the logic of this node, you can understand probably what it does. It tries to go to the goal by avoiding obstacles, right? This is a special node in the sense that we provide a combination of visual tool to define the node from a map. And then internally, this will be converted in this case into, I guess it's a vec3. Yes, a vec3, which is the latitude, longitude, altitude. But you can have other things like there is trajectory nodes. So if your node allows to have a list of waypoints, you can go to the trajectory node. You go to the configuration, you tell where you want to define the trajectory. Let's go to maybe Rome. These days, Rome is quite famous. Yeah, let's go to where you definitely cannot fly drones. So let's create a trajectory here. Boom. And what happens is that now this node has been configured with a list of waypoints with their own latitude and longitude. Maybe you want to go higher, I don't know, 15 meters, maybe 50, otherwise they shoot you down. Oops, so apply, and voila. So now we have all the nodes configured. So if you want, if your node allows, you can replace this map position with something else, which is now a vector of a vec3, so a list of waypoints, latitude, longitude, altitude, and you're good to go. Now, I want to show you, for those who like code, what happens inside this node and how to actually define such a node, right? So for doing this, I have to squeeze this and show you this instead, right? So This is the Intrepid Python SDK, which is available on PyPy. Again, it will be provided to you via the links. It's already it's open source and already available. And there is also some boilerplate code that we provide for you to define this particular node. Well, not this, but just an example. So if you can read a bit of Python, I believe everybody can read Python these days. It's pretty simple. So you define your node, which is, you import the Intrepid Python SDK with all the things that you need. In this case, we need a node. We define the node from a configuration that is right here. Very easy. A list of inputs, which are the inputs that you see. A list of outputs, which are the outputs that you see. If you want, optionally, you can define a QoS policy on the node. And then the server where that node is going to run. And more on that in a second. So once you have your node defined, if you make a mistake in the configuration, the system will tell you that there is something wrong. So don't worry. If there are incompatible inputs, outputs, etc., we will figure that out as much as we can, of course. Then you register your node to the service handler. Optionally, you can add a QoS policy to the node, as I said. And that's it. Then you register a callback, which is the function that you are running when this node is triggered, right? So basically, the Intrepid agent, once it executes this graph, it will trigger the execution of the graph. And once it triggers this particular node, the Intrepid agent will call the service that is actually executing that node, right? And so this means that you can run the Intrepid agent on a machine. Each node, if a node is very complex, it does heavy computer vision stuff, you want to delegate to a dedicated machine running the computer vision stack, you can pretty much do that off the bat. Why? Because here you just define where that node will be executing, and the agent will orchestrate that for you. Easy. Okay? So in the callback function, you can basically attach whatever you want. You can have an entire Python project doing computer vision, doing the smartest and the most complex navigation algorithms, whatever, we don't care, right? So this now, in this particular case, we just defined the DWA, which is a navigation system. It's called dynamic window approach. One of these undergraduate algorithms, but you're free to implement your own, and essentially attach the callback to this, register the callback to the service handler, and that's pretty much done. If you want to publish this node, I just realized that. Okay, let's see if I have that node here. I just realized indeed I don't have it here, obviously. So I will have a different node, but it's the same thing. So this code should be familiar, right? We have exactly the same. It's just that the signature of the node is a bit different because indeed it's another node. I will show you how to execute this node. So the only thing you have to do is, in this case, Python for tutorial Py. What happened here? You are registering the node. The node has a name, the one that I gave in the TOML configuration, inputs, outputs, and now says I'm waiting on 999 localhost, right? So what that means, it means that it's waiting for someone, the Intrepid agent, eventually, to hit that node and say, hey, I have a set of inputs for you. Now it's time to compute whatever is your logic and give me the outputs. Because from there, I will continue the computation on the graph and I will serve this graph successfully, right? So that's pretty much what you do. If you want to publish this node, you download the Intrepid agent and you write something like this: Intrepid agent publish the name of the node, where it is being served, and of course for security reasons we have a way to define a token that you copy from the dashboard. You copy there and you publish. This is an error because the node already exists probably. Yes, so I need to force that, and now the node is published, right? So this node is called tutorial 2. We can go probably here, tutorial 2. If I add this node, you should find the node that's been defined from Python. So this and this are the inputs and the outputs. And of course, now, if you execute this graph, this node, you have to connect the node to the rest of the graph, and it will work. Okay. So let's. So this is the how you define custom nodes. Let's say from SDK. How do you connect native nodes in combination with other custom nodes? I think it's time to move to probably ROS. So before we do that, maybe we want to do something else, which is the showing how the collaborative workspace works. But to do that, I need some volunteer. So usually these things are done via calls. So to do to ask for a collaboration, imagine you are working on this graph. The only thing you have to do is clicking this button here that will allow you to start a collaboration session on this graph. Okay, so do you want to start a collaboration? Sure. You get this super secret link, not really, and you call your best friend. So I have the luck to have Alex somewhere in Europe. So let's see if he's online. And he can help me. There you go. I hope he's not sleeping at this time of the day. Let's see if that works. There you go. Hello there, Alex. I think I have a nice link for you. So here is the link.
Hello.
All right, cool. So I just give this link. Now, Alex, of course, has an account on Intrepid AI. And here we have a collaborative widget in which we should find Alex joining anytime soon. And effectively collaborating on the graph. Let's see if that's true.
You see the login page, right?
Yeah. This is gonna be so much trouble. Let's see.
Trying to find the passwords.
So you should have the link in the chat.
Let me copy the link again, just in case.
Yeah, you're here. Okay, so maybe, maybe you want to help me out with whatever. I don't know, I can start moving stuff. There you go. Well, you get it, right? It's like everybody's doing his own thing. And what happens here is that we keep revisioning the graph. And of course, you have the full collaboration. You can have users collaborating on the same graph in a non-destructive way. So you can go, you can keep versioning the graph and go back and forth in the graph history. All right. I guess you're creating stuff somewhere here. I see you. Okay, Alex. Thank you. So once we are done with that, so I think I'm the owner of the collab session, so I can stop the collaborative session. Thank you so much, Alex. I'm gonna close this call now and continue. We have stuff to do. Okay, so I stopped the collaborative session. You want to, yes, okay, and now I'm back to my previous version. That, by the way, is being versioned right here. So I have access to all the versions that I might have regarding this particular project. Okay. All right. I think it's time to move on to ROS integration. So for ROS integration, we can close this. So there is this amazing ROS logo right here on the sidebar. That is, in fact, the ROS bridge. In order to see ROS in action, I need to have something running in ROS. And guess what? I do. Right here. So imagine I am... so the first thing I need is, of course, running my Intrepid agent. Wherever I'm running ROS, that will run the bridge. And what happens is that I can... now imagine that what you see on the right, it's happening on another machine. We should not have access to that, right? We just have ROS in the air. So what you would do is click in the ROS bridge, and then all of a sudden you find, there is in fact a connection that it was probably cached, but there is a discovery service that tells you, hey, there is something about ROS here. So let's see what. So in order to, now there is nothing yet. So in order to show ROS in action, let's run one of these demo nodes. There is the listener and the talker in ROS. So I guess it's ROS2 run demo nodes, the Python version talker, I think, that is publishing to a topic. And as you can see here next to me, we have populated, like this service populated the ROS ecosystem with the ROS services, ROS nodes, the talker, indeed, the topics right here. So they are all available. So this means that I can see a ROS ecosystem in present. So what I might want to do, for example, I create a generic graph that says I want to create let's say, a ROS subscriber, okay? So basically we have someone in ROS publishing, and I create a subscribe. Of course, I don't remember what is the topic. I click here. The discovery service knows that there is a chatter topic somewhere in the ROS ecosystem. I select that. I take a debug log. The debug log is essentially the equivalent of a printf for those who print stuff to terminal. And we connect whatever is the message received by the subscriber to the debug log, right? So I would save this. I have delete me, let's say 3. I save this graph, and I can execute this graph. So what happens now is that I should see messages coming from ROS into Intrepid. Okay, so here on the right you see hello world 80 something 100, and here are the messages that we actually receive. Now these messages, of course, can be consumed in the rest of the graph, whatever is the logic that you are implementing. At the same time, we can do a ROS publisher, for example. So I want to publish to the same chatter topic. We can do this on a timer, let's say at 5 Hertz. And we want to print the message, hello from Intrepid. And now, of course, on this side, we should have a listener. So this is running on ROS in Python somewhere else. In fact, it's another machine for real. So we have the listener now. And I guess I can, well, I need to save this and play. and we start receiving hello from Intrepid 5 times per second. In addition to this other, we are subscribing to the same topic, and of course we receive them from both, right? So all this is essentially hiding all the complexity of ROS and of course DDS. We are adding also Zeno as a first-class citizen in Intrepid, so that you don't need to bother with the network protocols and all that stuff that comes up pretty much every week. All right, so I guess we can shut down these ROS nodes and also this and keep going. Which brings us to the Intrepid Simulator. So let's start having fun now. All right, so what is the Intrepid Simulator? Intrepid Simulator is in fact probably one of the most complex components that we have built so far. That is essentially a game development engine that uses a different technology from the one used by video games, usually Unity or Unreal Engine. These are amazing engines, by the way, but for simulation, there is another paradigm of computation which is called ECS, Entity Component System, that is more indicated for large number of entities in simulation, especially when you need accurate physics. In video games, usually you don't need accurate physics. You need playability, and you need to have fun. You can have fun also in robotics, but you also need the physics. The nice thing of the simulator is that it's fully customizable. It's not yet available, but you will have the possibility to bring your own physics model, your own controller. Even next week, we're going to release the import your robot model via URDF or via GLTF or GLB. If you know how to play with Blender, you can bring your own robot with that. So there are all these possibilities, extremely flexible, because there are also no integration hassles, in the sense that we believe a simulator should be as simple as clicking on an icon, let's say, or running a command. All right. So that's what we believe a simulator should be. And all of a sudden you would have something running. Okay. So before we get there, let me finish on this. A very unfair comparison between Gazebo and Intrepid Sim. Well, of course, it's faster. It's very modular, much more modular than Gazebo, because we have designed and engineered with other requirements in mind. Of course, it's an unfair comparison, because Gazebo is very complete. So if you really need a full spectrum of robotics controllers and robotics sensors, especially, Gazebo is still a very good shot. But if you are dealing with, for example, swarm robotics, we have tested this, and I will show you this in the demo. Very large number of entities for which you really need to visualize the behavior of multiple drones. As you can see here, I'm running at 60 FPS with 9 drones or 8 drones, I don't remember. Yeah, 9 drones, no matter what. So I will show you later also the amount of flexibility that we have designed and implemented, and also the way you can control this via Intrepid or without Intrepid, with Python SDKs, there is a WebSocket in between, so there is a network in between, and you're free to use pretty much whatever you need. In order to understand, if you guys want to understand better what is ECS, there is another free download for you. You can take it from intrepid.ai/notes, where we explain, I hope I did a decent job to explain how ECS works and why it is better for simulation. So there is, of course, once we launch the Intrepid Simulator, as you can see here, there is an empty world. There is a bit of atmospheric fog probably, but that's pretty much it. So one thing that you can do, of course, is pointing to your vehicle and start controlling it. You can control it manually, as I'm doing now with the WASD, if you call it like that, WASD. Gamers know what I'm talking about. Let's show some trails. Show the closest object, and let's go back home, right? So what I'm doing here, as simple as sending commands to the robot, and there is an hard-coded controller inside that is mimicking the Crazy Fly controller, which for the record is terrible. Sorry, Crazy Fly. But yes, you can control the same vehicle, of course, with an autonomous stack outside of the Intrepid simulator, no problem, as I will show you in a minute. You can, of course, pause, you can start recording telemetry data, you can do post-mortem analysis, all the things that you expect a fast simulator should be doing, right? We think that, however, there is something else that you should see, which is what we call the CityGen feature. So this is our version of the procedural generation of a city. So you can pretty much decide how to randomize, if you want to randomize. You can also create these cities yourself via code. Or you can decide, for example, what is the city layout or topology, I think it's called, that you prefer the most. There are some folks who actually love linear cities these days. You can also do that. So let's make something more realistic. Don't know, maybe something like this. Man, that's too small. Let's do this. Voila. So what you see here is intersections of roads, buildings. We can generate also, I think, trees right here. So the good thing of this is that when you start the simulation, all of a sudden you start rendering the entire world as it was on the topology. So if I zoom out enough, you should see the same topology there. So we go down to the agent, which is our vehicle. And what happens now is that this thing can already collide. Oh, let me follow that. So can already collide to any of these buildings here. Now, don't expect explosions. We didn't do that. We hit and we despawn. So when we detect a collision, we print it here down. Probably you missed it. It was here. We return that to a telemetry system, so you can handle that, monitor that collision, and decide what to do with that. We simply despawn as a default action, so we despawn the vehicle once after collision. So in order to show you the capabilities of the simulator, I need to introduce you to the next big kid, which is the Intrepid Python SDK. Again, same thing, it's still on PyPy, the same Intrepid Python SDK that you use to create nodes, you can also use to interact with the simulator. So let me show you how easy it is to interact with the simulator with a bunch of examples that I'm gonna drive you through this presentation. So in this particular script, this is the easiest of all. You import the simulator. Again, super simple Python. You declare the simulation, you connect, and that's it. You are now connected to the simulator. This is not super fancy, but let's assume that you want to get all the entities in your simulator, in your simulated world. You would do a connect, sim get entities, you get the entities. This is a Python object, it's a list. You print them, you get all the vehicles, it's another list, you print them, right? So let's see. I think it's here. So Python, what was it called? My memory, get entities. We have 7,576 entities and indeed 4 vehicles, right? If I want to get a particular information about a single vehicle, we are on agent 0, I think. So we connect to agent 0. And of this vehicle, we want to print the local position, the rotation, acceleration, angular velocity, linear velocity, the full state. We try to get a non-existing vehicle and see what happens. And then we print everything. That's, I believe it's very simple Python. I hope it is. So if we do Python get, I think it was vehicle. There you go. So vehicle ID 0, this is the internal name of the vehicle. We are very creative in assigning names and all the vectors that you expect, the positions, rotations, accelerations, etc. Okay. We have the concept of abstract sensor. What is the abstract sensor? Is a sensor that can perceive the obstacles around the vehicle. We have built this, which is needed by some folks at university. So they want to interact with the buildings that the obstacles in general that they have in the simulation. Oh, by the way, if you are not happy with this layout, you can, readjust it as you wish. So you can move things even during the simulation. So imagine you want to, a little digression here. Imagine you want to, let's say, test the behavior or your computer vision algorithm, let's say, and see, hey, imagine if there was a tree right, there instead of there, or right in the middle of the street, what would my algorithm do when, there is something unexpected? So you can create these things, and you can procedurally generate them, and you can reproduce them deterministically. So you can write scripts for testing simulation. So you can run the same behavior into an infinite number of worlds, in fact. Okay, so, little digression, sorry about that. Now, back to the abstract sensor. You define the radius, and you say, hey, of this abstract sensor, I want all the obstacles. So there is a list of things that you can ask, all documented on docs.intrepid.ai, later in the links. You can provide a vehicle, etc. And so you get the point. So if you run this thing, you should see for agent 1, I don't know where agent 1 is, right here. So I guess we can see a bunch of, let's try. There you go. So Intrepid Sim, localhost connected. These are the entities that I found around me in the range of 50 meters. Okay. There are, in fact, 4 obstacles, 1, 2, 3, 4, 5 obstacles, and these are their positions. So as you can understand now, I'm getting more and more complex. I move to the, so we can essentially detect things in the world. What's next? Interacting with the world, right? So there is this, the idea of executing something at every X milliseconds. Let's say you are driving this vehicle in sim. You want to read sensor data. You want to process this sensor data. Imagine you have a navigation system, and then you want to send information or velocity vectors to your velocity controller. And you want to keep doing this until whatever is the stopping condition, right? So you can do so with the sync function. So again, sim connect, you can define your step duration, and then you use the sim sync. And in the sim sync, the same thing as the Python nodes, remember the function callback, my control foo, this function is yours. You can do whatever you want, right? You can add an entire Python project, an entire computer vision stack, or whatever. We don't care. This is real, normal Python, in fact. There is no magic. So you have your entry point, which is the callback, my control foo in this case. And what happens in there, in this case, I'm doing something extremely stupid, which is spawning UAVs at position 0. So what we should find is that when I run this simulation, it's hard, it's a bad word. We should see a bunch of UAVs getting spawned from the same position and probably colliding with each other. So we release, there, I saw it. There you go. These guys are making drones. Of course, here they all collide because, they get despawned, they get spawned and despawned because, as I said, the default behavior is to despawn on collision. Some can still make it. There you go. Those guys are in the field now. Nice. Okay. Something a bit more complex. Let me show you how to spawn a camera. So again, very simple. You get a vehicle ID 1. In this case, I better restart my simulation because vehicle ID 1 probably crashed. Okay. So I get vehicle ID. I get my vehicle. On this vehicle, I say spawn camera on the vehicle. I provide position and rotation relative to the vehicle. And then I provide also the resolution of my camera, the grabbed frame. field of view, and the format if I want. So I get this camera object now. I pass the camera object to my control function, and I say here, I want to keep capturing and convert this to an image PNG and whatever, and watch it. Okay, so if you run this thing, subscribe and grab. Okay, now there is no real output. Probably there should be an image somewhere here. There you go. But I want to do something even more crazy, which is, let me close this, subscribe and grab navigate. You probably understand what this does. So we, very similar to the code before, we spawn our camera. In our control function, we try to navigate and following waypoints. Okay, again, something trivial for you guys, I know. You can add whatever algorithm you want. We are not good at running navigation systems. We are good at writing tools to build navigation systems. So what this thing does essentially navigates through the waypoints and grabs a video footage image by image. All right. So let's try to see what happens. Like that. So as you can see, we spawn. Let me see if I can show you this. I think we can. And there you go. I am navigating through waypoints. So this is my simulation. I can be anywhere. Maybe I can put a pause, show a trail. And yeah, I think I can even move. Oh yeah, I can move this drone and the video footage will go accordingly. Now, of course, if you want to control multiple vehicles, we have 4 in this simulation, you can just launch 4 different scripts from the same machine, or if each script is very heavy, from different machines, because each of one is dedicated to executing the behavior of each single robot, you can perfectly do so. So you have this, separation of concerns, as I will explain in a second, and then close this presentation. So I guess we can stop the simulation and go back to the last part and the conclusion of the presentation, which is this. So the simulator, I was just saying, is a set of components that can be decoupled completely in any possible combination. So you can, in fact, run the simulator or the dashboard, the Intrepid agent, and whatever is your node, your Python node in this case, like the navigation logic, the computer vision system, whatever, you can run on the same machine, or you can run on separate machines. There's no difference from an architectural perspective for Intrepid. So you're free to choose whatever is the way you distribute algorithms, decentralize them or centralize them on one beefy machine, up to you. So that's what we mean by an enormous amount of flexibility. In the logic, you can run whatever. You can run Python nodes, you can run ROS nodes, you can run native nodes, custom nodes, JavaScript, why not? So that's pretty much it. So this is the Intrepid Python SDK that you can already find on online at this address, or pip install Intrepid Python SDK will also do the trick. That's it. So this is the list of links. Of course, I will make this presentation available online on our website, intrepid.ai. But these are the most important links that we believe are also important for you. Also, I think the most important of all is the Discord, because we are there and we are always happy to interact with you and answer the most technical questions you might have for your project, and very happy to help there. That's it, pretty much. Very last thing, we are going to be, these are part of our partners, and we will be also playing a bit the hard games at at the Battlefield of Things 2, which is a hackathon organized by the Belgian Defense this year in end of May. So we will be there. We don't know yet what we're going to build, but we have some ideas. So more on that another time. Thank you so much. And of course, if we still have some time, I would be very happy to get some questions, if any. Or otherwise, again, there will be some space definitely on Discord, where Alex and I are usually quite active. As long as the program logic is encapsulated in the entry point, are we free to run anything normal Python can, API calls? Absolutely yes. So indeed, we had an experiment with the communication protocols, so network protocols. Instead of using our own from the Intrepid library, you can pretty much decide to implement your own sockets in Python. Maybe you have them already. Absolutely, yes. So these two things can be combined. The Intrepid agent is just an execution layer on the vehicle. All the requests that you make from the vehicle using whatever library, you are free to do so. So if you have Python or Boost in C++, you can, yes. For the Discord channel is on Intrepid AI. You can definitely go here. There are all the links that you need. Discord, GitHub, and there is a blog that we maintain when there are also new features that we announce. It's a newsletter. You can subscribe. We don't spam, of course. we send one newsletter per month or less, unless we have really cool features that we want you to have a look at. Thank you. All right. Thank you so much, folks. Thank you for taking the time. And of course, I enjoyed this very much. And yes, we'll come back in June because we are going to add other additional features, especially to the Intrepid agent and to the simulator. We really are hard working on that. We're not revealing anything because we're running internal experiments about that, but we'll definitely announce it as soon as we are ready. Thank you so much, everyone. Have a nice one.